Hi, I'm Cody. This is the Church of Logic, and I'm here to present the proof of the Kruskal tree theorem. So last time I explained kind of what the embedding order in trees was. I mentioned that if the labels on the trees are finite, then the embedding order is a well quasi-order. I explained what the well quasi-order was, and I said it was kind of hard to prove this theorem. It is actually the case. Okay, one thing I want to mention: the order, the labels, the number of labels has to be finite. But it turns out that what you can do is say that the labels aren't necessarily finite, but they are well quasi-ordered by some order. All right, and then you change the embedding relation to be instead of taking a node and removing it and gluing one of its children to the parent. What you can do is just change the label to that node to a smaller label in the well quasi-order on labels. Right? And now you take those two operations, you take the transitive closure of those, and great. Kruskal's theorem says, oh, actually that's also a well quasi-ordered. And it turns out that, in some sense, that's the same thing. Well, that's the same thing. That is a strict generalization because a finite set with the trivial order, where two things are ordered if and only if they're equal, is a well quasi-order. Right? That's actually the pigeonhole lemma exactly, because they're saying if I have an infinite sequence in some finite set, eventually I'm going to get a repeat, a thing that's exactly equal to a previous element. All right, and so finiteness is this very strong well quasi-order, right? And so in some sense, well quasi-orders are a generalization of finite sets, right? You can think of a well quasi-ordered set to be kind of a super finite set. And I kind of like that idea because what computer scientists and logicians are trying to grapple with is the relationship between the finite and the infinite, right? We only have a finite number of symbols. We can only know a finite number of things. We can only look at, finite counterexamples, and then what can we know about the infinite? All right, let's get down to brass tacks. The proof of the tree theorem is going to proceed in a number of steps, and all of these steps require cleverness. So fundamentally, the proof is going to be by contradiction. You're going to assume that trees are not well quasi-ordered, and we're going to get some contradiction. We're going to do a number of things and get a contradiction. Now, in cases like these, it's often, you often want to prove that something is true by contradiction. You assume it's false, right? And when you're trying to prove a for-all statement, like everything has this property, right? Every infinite sequence has one element which embeds into a later element, right? When you assume it's false, you're basically assuming the existence of a counterexample. And then what's a common move in mathematics is to start studying that counterexample as if it existed. Like, take it seriously, look at the counterexample, deduce properties from it, examine it. And then eventually you start breaking things, showing really bad properties, weird ones. And then eventually you get a contradiction, hopefully. In the case of hyperbolic geometry, it's kind of amusing. People assumed that, for example, the parallel postulate was false. And so they would assume its negation, and they would try to find these contradictions by getting more and more pathological examples. But of course, in that case, they failed, right? All these pathological examples actually exist. But in our case, it doesn't. So we're going to assume the existence of such an infinite sequence of trees such that none of them embed into later ones. And eventually, yeah, that's going to lead us to a problem. And okay, because these are things we're going to study for this whole proof, we're going to give them a name. And the name of such a sequence that contradicts the well-quasi ordering is called a bad sequence. And people will often talk about bad sequences and try to understand their properties. So let's take a bad sequence of trees and get a contradiction. Now, there is so there are several facts about bad sequences. One fact is that you can drop anything from that bad sequence as long as you get an infinite number of remainders, right? You can drop like every even member or every odd member or like every member that's not at a prime position, and you still have an infinite sequence, and that infinite sequence still has to be bad, obviously, right? You if you didn't have any term that embedded into a later one, then dropping a bunch of sequences doesn't really matter. All right, we're going to use that fact later. The second thing we're going to do is show that if there is any bad sequence at all, then there is something called a minimal bad sequence, right? We're going to basically define an order on sequences and show that there's some like smallest such order in some sense. But it's not uniquely smallest, but it is smallest, among, this order of sequences. That was a little clunky. Let me explain what I mean. Basically, what I'm going to say is, suppose you have a bad sequence, then there is, a bad sequence such that at each position in that sequence, right, the term at the nth position that I'm called t of n, let's say, or the tree at that nth position, is the smallest possible tree for that sequence that is, the first element of a bad sequence that continues on from that tree on, right? Now, what does that mean? It means that if I have a bad sequence and I have t of n at some position, any sequence with a smaller tree at that position in size cannot be the beginning of a bad sequence. All right, and how do I prove that? Well, I'm going to do it kind of by induction. I'm going to say at each position, let's suppose I have a bad sequence, and let's suppose it's minimal up to position, t of n, which is to say there are no trees at positions previously that I could replace with a smaller tree and still get a bad sequence of that size. And at t of n, I'm going to say, okay, well, is there a smaller tree at that position that starts a bad sequence? If yes, then I take that one and I take the bad sequence. And if not, then I'm done, right? And then I continue with the next term of the bad sequence, and I do that same operation. And I do that operation an infinite number of times at each n. Now, astute listeners might notice that just doing this operation, just proving this existence of minimal bad sequences, actually uses some form of the axiom of choice, which is a little bit unfortunate. And there are some deep reasons why, having these kinds of minimal bad sequences requires some powerful form of reasoning. But all right, let's take that on faith. There are minimal bad sequences. There are bad sequences such that at each, n, that t of n can't possibly have been replaced by a smaller tree in size. Great. Okay, infinite bad sequence. Now, we need to take this minimal bad sequence and find a contradiction. And we're going to do that in 2 steps. Now, the first step is, what would be a lemma in a textbook. Basically, we're going to shave the heads off of all of these trees. We're going to take off the first term, and then we're going to take the remaining subtrees, and we're going to throw them in a big bucket of trees, right? And it's an infinite bucket, roughly. If the tree is already a leaf, if it doesn't have subtrees, then we'll just remove it. We'll not even put it in the bucket. But if it has subtrees, we're going to put all those subtrees in a big bucket. We're going to collect, for that whole sequence, collect all those immediate subtrees and put them all in this big infinite bucket. And that bucket only contains kind of strict subtrees of the original sequence. All right, now the lemma says this. If I only take trees from that sub-bucket, I cannot form a bad sequence, all right? Which is to say, the trees from that sub-bucket, from that bucket of subtrees, are well quasi-ordered by the tree embedding. Okay, this sounds kind of obvious by our kind of minimal bad sequence argument. It's like, it's minimal, you're taking subtrees. It can't possibly be a bad sequence because, you know, you've kind of excluded them by definition. But that's not true. This bucket, right, the minimality only applies to the exact order in which I created that bad sequence. I'm allowed to use any term in that bucket in any order I want to form any bad sequence I want. In particular, I can take, you know, way bigger trees if I want to start with, and then even bigger trees to continue with, and I can do it in some completely out of order way. So yeah, the minimality of the original sequence. We're going to use it, but we can't use it trivially. We can't immediately conclude that the terms in those subterms in that bucket are well quasi-ordered. So, okay, so now we need to do a little bit of work. We're going to assume that there is a bad sequence, you know, that just uses those subtrees. Okay? And now we need to get a contradiction. Okay? Take a bad sequence. The first element of that sequence is a subtree in the original sequence. Let's say it appears at position k, right? So at position k, that first element in the sub-bad sequence appears in the first bad sequence. Now what we're going to do is drop in this new bad sequence all the elements that are subtrees of terms that appear before position k in the first sequence. By the way, maybe I should have written this down. I'm taking this proof from the excellent book called Term Rewriting and All That, where they prove it in like chapter 2. So term rewriting and all that is this really foundational source for term rewriting theory. And I'm also not sponsored by them, but I'm taking this proof directly from there. Okay, so we take the sub-bad sequence, we take the first term of that sequence, it appears in the original sequence at position k, and now from the sub-bad sequence I'm going to remove all subterms that appear before position k in the original sequence. Now this has to be a finite number of terms because, you know, before position k there's only a finite number of terms and there's only a finite number of subterms. So I'm only removing a finite number of terms. And because my sub-bad sequence is bad, it contains an infinite number of terms. And so certainly I've only removed a finite number. And so it's still infinite. And so it's still a bad sequence. I removed a finite number of terms from a bad sequence. I still have a bad sequence. Okay. Now if I take the original bad sequence, right, t1 to tk plus 1, etc. Now what I'm going to do is I'm going to truncate that t1 tk at the kth position and glue in this sub-bad sequence at that position. All right. I'm just going to do kind of a surgery operation. Now because the thing I've removed is the tkth element, and the thing I've glued in front starts with a subterm of tk, there I can use my minimality assumption. And I know that this new sequence, because I've replaced it at position k by something smaller, a subtree of tk, I know that this cannot be a bad sequence. It just can't. That's where I use the minimality assumption. And so this new sequence, t1 to tk, and then the sub-bad sequence with the, you know, the first the pre-K elements removed, is a good sequence. It's not a bad sequence. And therefore, there are two positions in that sequence such that a tree at the first position is a subtree embedded in a tree at the second position. Okay, it's a good sequence. And it's pretty easy to see that because I built a good sequence of gluing together two pieces of bad sequences, these two positions where a first tree is embedded in a second tree, the first one has to be in that first K, and the second one has to be later. All right. And now contradiction is if you examine that fact, the fact that one of these TKs has to be smaller than one of these later subtrees, you'll see that contradicts minimality of the bad sequence. And in particular, it contradicts badness of the first bad sequence. And in particular, any one of these embeddings will result in an embedding in the original tree. And that is a contradiction because we assumed that original tree is bad. Great. Okay. So that's the lemma. All right. So we've only made partial progress. We've proved that this bucket of subterms, that is well quasi-ordered by the embedding relation. Okay. So that's kind of okay. That's that. If I was the one coming up with this proof, I'd be a little bit discouraged here because I've done a lot of work and I've only proved that these subtrees are well quasi-ordered. I haven't proved anything about the original bad sequence yet. But we are making progress. All right. So now we take this original bad sequence. Now it is pretty easy to see that you can't really have an infinite number of leaves, all right? You just can't. There's only a finite number of labels, and leaves are just a single node with that label, and that's it. And because we only have a finite number of labels, like I said, the pigeonhole principle says eventually you'll repeat a label, and then the tree embedding says, oh, those two are embedded. We assumed this was a bad sequence, so we can't have that. All right, so we have only a finite number of labels, everything else is non-labels. And if you look at these trees that are not leaves, you'll see that the top label, the label at the very top of that tree, if the tree is growing downwards as it traditionally does in mathematics, the top label of that tree, again, you're going to get repeats. You're going to get at least one label that's repeated infinite number of times. Okay, so now we take that subsequence. And like I said, that label is repeated an infinite number of times. We have an infinite number of those trees with that first top label. Let's say it's the label F. I don't know. And so we've removed a bunch of those trees from this sequence. But we still have an infinite number. And so it's still an infinite bad sequence. And now we can look at just the immediate children, and we take the tuple of immediate children of that top F label. All right, so that's a sequence of tuples of trees. Okay, but those trees and those tuples are from that bucket in the lemma. They're all taken from that bucket. And it turns out that if you have a well quasi-order, then taking tuples of those things is also well quasi-ordered. Which is to say, if you take an infinite sequence of tuples, then there are two tuples in that sequence such that each element is less than each corresponding element in the later thing. So if you have pairs, you have an infinite sequence of pairs in a well quasi-order. There is some pairs such that the first and second projection are both less than, or are each less than the first and second position respectively, right? So the first one here is less than the first one there, and the second one here is less than the second one there. And same for any size tuple. This is actually non-trivial. That well quasi-orders lift to tuples is like a real lemma, and I also invite you to prove that. It's proven in the book, and I'm going to give the reference, but it is really a non-trivial fact. You have to do it by induction, and it is not immediate that these tuples are going to be well quasi-ordered, but they are. All right, so I've taken, tuples of terms from subbuckets. I know that the subbucket is well quasi-ordered. Therefore, the tuples are well quasi-ordered. And therefore, there are two tuples where each element in the first tuple is embedded in the corresponding element in the second tuple. Okay, but that, combined with the fact that I know that the top node has the same label, means I can just glue the label back on, take those two tuples, and I've just added the same label on both sides. Therefore, because all of the children are embedded in all of the children on the other side, and the top label is the same, then those two trees also are in an embedding relation, which is kind of cool. And that's my contradiction. I have an embedding in what I assumed was a bad sequence. Therefore, the sequence was not bad after all. It's a good sequence. So that's pretty cool. I don't know, that concludes the proof. And you've seen that I had to do these awkward steps where I take, infinite subsequences, and I have to find, well quasi tuples instead of elements. So each of these steps feels very complicated combinatorially and also very powerful. You might get really, really long sequences before you find these tuples. So yeah, I mean, this is true, and obviously, has been repeated on Numberphile and by myself many times. These sequences can be really, 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 really long, and so long, in fact, that that their length can't really be expressed concisely using, finitary arithmetic. This whole proof can be carried out pretty trivially in second order arithmetic. Like, every step is not that dramatic. I did say we used a form of choice, but it's a weak form of choice where you don't actually need the axiom of choice. You can just sort of prove this thing that's a little bit awkward to prove. And then you can carry out all these steps involving bad sequences, minimal bad sequences. You can all carry them out in second order logic. So second order logic can prove tree theory exists. It can prove tree of n exists for all n. And yeah, but much stronger subtheories can't prove that. And hopefully I'll talk about exactly why in some later blog post. But until then, take care.